Hello.
Hello, welcome to this video. Today we're gonna derive a formula of squares in a rectangle. First, let me explain where it came from in the original problem. So I saw this Mathologer video. I'm gonna have the link in the description. And he had a challenge for the viewers to find the formula for the amount of squares in a square grid with size endpoints by endpoints. And after finding that formula, I decided to challenge myself and go for a rectangle with A points by B points, where A is greater than or equal to B. So before we get started, this is the original problem with square of n by n, and there are a lot of types of squares. There's this square, there are more squares. If you look closely, you might just notice this square or this square. There are many squares in the square. In fact, in this 5 points by 5 points specific square, there are 50. And I will derive the formula for the rectangle instead of the square, a more generalized thing. So now let me erase the board, and then I will explain what we'll do and all of that. Okay, so this rectangle with sides A by B, where n is greater than or equal to B. By the way, don't forget this. This will be very important. It's not just something. The formula is very different as if B is greater than or equal to A. So now, let me say a few things before we get started. So, we're going to refer to A and B as the length in units. So maybe in this specific example, A is not 5 points, but it's a length of 4 units. And similarly with B, in this specific example, it's not 4 points, it's a length of 3 units. And then later in the process, I'm going to replace A with A minus 1 and B with B minus 1. So A will represent the number of dots and not the length in units, and similarly with B, will represent the number of dots and not the length in units. That's the first thing. And the second thing is to see how many squares are there in the outer part of a square with length n. So let me show you what I mean. So say this square, just the outside part, and of n by n, how many squares can we draw? Well, we can draw the outside thing, of course, but if you look closely, you might notice this square and this square. They don't look like squares, but that's just because my drawing is bad. Imagine they are. So there's obviously the big one. So in this specific case of 3 by 3, there are 3 squares. And I won't do a rigorous proof, but in fact, in a square with n by n, length in units, with just the outside part, you can draw n squares. Similarly, each time rotate it by a bit to get the next square until the next rotation will give you a square that you already had. So now, let's see what we're going to do. We're going to we'll see how many 1 by 1 squares there are, how many 2 by 2s, 3 by 3s, and so on until the biggest square we have, which is B, which is length B, since A is greater than or equal to B. And then we will multiply by the side of the square, since that's how many tilted squares you can make out of the outside part of that square. So let's see. How many 1 by 1 squares? Well, pretty straightforward. I'll actually, if you mark the centers, and so on, you will have a rectangle with A times B amount of points. And then for the 2x2s, if we mark the centers, so this, 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 and this, it will make a rectangle which has A minus 1 times B minus 1 points. And it will continue like that. For the 3x3 square, it's going to be A minus 2 times B minus 2. 4x4, A minus 3 times B minus 3. And so on. Until the biggest square we can have, which we have A plus 1 minus B amounts of it. So let's write that down. The amount of 1 by 1 upright squares is, like we said, A times B. And then we multiply by like we said, by the length of the square, by its size. I already said that, I won't repeat why. And then, for the 2x2, we have A minus 1 times B minus 1, then times 2, and we'll continue. A minus 2 times B minus 2 times 3, A minus 3 times B minus 3 times 4, and so on, until the biggest square we can have, which we have A with size B, which we have A minus B plus 1, sorry. Well, I will write that differently. A plus 1 minus B of, that's how many B by B squares. And I'll actually multiply this by B plus 1 minus B, and then multiply by B, like we said. And notice, B minus B is going to cancel, and then times 1 won't change it. So I just added this so it will be more symmetric and more like the others. And now, we want to write this as a sum. K goes from something to something of something. Because things look very similar, like A goes to A minus 1, then A minus 2, A minus 3. And this goes up by 1, 2, 3, and so on to B. And that's actually something I want to address. We have 1, and 2, and 3, and 4, up until B. So we have B, So we have B terms in the sum, meaning we can let the sum go from 1 to B, since this will have B terms as well. Now let's see what's the inside of the sum. Well, you see, in the first term we multiply by 1, second term by 2, third term by 3, and so on, till the B term, which will multiply by B. So we will have in the sum multiply by K. And now, what we will do is, well, let's see. Now we need to write down how this A minus 1, B minus 1, and so on. And you might notice we can write this as A plus 1 minus 1, B plus 1 minus 1. And this is, well, A minus 1, B minus 1. And then this will actually be A plus 1 minus 2, B plus 1 minus 2. Then A plus 1 minus 3, B plus 1 minus 3. So we can say that we multiply this for the kth term. It's going to be multiplied by A plus 1 minus K, and then times B plus 1 minus K. And that's it. That's the sum. But remember, the answer to this won't be the formula, since A and B still refer to the length in units, and that's the points. But now it comes the part where we replace A and B with A minus 1 and B minus 1. Since here we'll get a nice cancellation. A plus 1 will become A, and B plus 1 will become B. So, the sum that actually will give us the answer is the sum as K goes from 1 to B minus 1, since it was before B, now B turned to B minus 1, and then times K. A plus 1 will turn to A, so A minus K, and B plus 1 will turn to B, so times B minus K. And I don't know if there's a better way to do it, but what I did was factor this out and use the formulas for the sum of first powers, second powers, and third powers. So the sum from k goes from 1 to b minus 1 of, say, k, or I'll write it as s of 1, is going to be, remember, to b minus 1, is going to be b times b minus 1 all over 2. S2 is equal to b times b minus 1 times b minus 1 times 2, times 2b minus 1 all over 6. And S3, the sum of cubes, is b cubed, not b cubed, b squared times b minus 1 quantity squared, imagine this is the 2, all over 4. So those are the three sums. And notice, hey, write this maybe bigger. So, notice, each one of these sums is a nice multiple of b times b minus 1 over 2. So after factoring it, we'll take out a b times b minus 1 over 2. So, first of all, let's factor it. So it's still the sum. K goes from 1 to b minus 1. And now, let's see. For the k cubed term, the only way we can have k cubed is k times negative k, which will be 1k cubed. The coefficients is, well, 1. Now for the k squared, well, the only two ways we can have k squared is k times negative k times b, or k times a times negative k, and those will become minus a plus b. So that's the coefficients, negative the quantity a plus b, and then times k squared. And for k, the only way we can have k is k times a times b. So we had it with ab times k, and we can't have any constant term since we multiply everything here by k. Can't have any constants. And now we'll use these formulas, and like I said, we'll take out a b times b minus 1 all over 2, and then let's see, taking a b times b minus 1 over 2 from here will be b times b minus 1 over 2, and I'll actually write this as b squared minus b over 2. And then for the k squared, we have 2b minus 1 over 3 after taking out the b times b minus 1 over 2. And then remember, multiply by the coefficients. So minus a plus b times 2b minus 1 over 3. And then plus, we'll continue here. With the k, we just have b times b minus 1 over 2. So taking out, well, b times b minus 1 over 2, we'll have just the 1. So, in the sum, we just add the coefficients. So I won't confuse you. So, plus AB. This is continuation of this. And now, I won't actually expand this. You can do it on your own as a fun little exercise or something, but I won't do it. It's it's a lot of algebra, but what you end up, it's not a lot of algebra, but it's still some. But you can do it at home, I'm sure, alone. And b times b minus 1 over 2, and then this inside the brackets will simplify down to, it's going to be times b plus 1 times 2a minus b all over 6. And now 2 times 6 in the denominator will turn to 12. And then we'll have, as a difference of squares, b minus 1 times b plus 1 will be b squared minus 1. So, we will have b times this times that, which is b squared minus 1, times this, which is 2a minus b, and then I'll lower this times this, which is 12. And that is our formula. And before I end the video, you might notice that if a is equal to b, we'll have a square. And then plugging in here, we'll derive the formula for the amount of squares in a square just from this. So this is like a more general formula. And if you want more interesting content about math and this sorts of stuff, subscribe to my channel. I will upload soon a lot of more interesting videos like this one. And that's it.